For centuries, the university lecture hall was a sanctuary of scarce information. If you wanted the facts, you had to be in the room to hear them. Today, factual information is ubiquitous and instantly accessible. This reality forces a shift in higher education. The professor's value moves from transmitter of truth to architect of the educational experience. Standard instructional design models, like ADDIE, try to organize this experience. They map out the logistics of a curriculum, analyze, design, develop, implement, and evaluate. But while these models dictate a course's structural sequence, they ignore the internal psychology of perception. They offer no mechanism for how an external event actually becomes internalized knowledge. This is where David Kolb's experiential learning theory steps in. Far from being a soft pedagogical philosophy, Kolb's model operates as a rigid cognitive algorithm. Kolb defines learning through action. Knowledge is created through the transformation of experience. You have to grasp the sensory experience, and then you have to metabolize it. True learning is a biological event. To build complex, lasting professional competencies, we have to stop designing courses based on corporate flowcharts and align our instruction with the actual physical architecture of the human cerebral cortex. Kolb's cycle is driven by the resolution of dialectical tensions. The first is the axis of perception, the cognitive conflict between immersing yourself in the physical sensation of an experience and stepping back to analyze it logically. You can't do both simultaneously. This diagram illustrates the second tension, the axis of transformation. Here we see the conflict between internal, reflective observation, gathering data, and active experimentation, where you physically intervene in the world. In 2002, biologist James Zull mapped Kolb's theoretical grid directly onto the physical anatomy of the brain. He showed that this pedagogical cycle is how a neural network forms. Stage 1 is concrete experience. Information enters through the senses. A monotone lecture barely registers in the auditory cortex, but rich multimodal input, visuals, physical manipulation, emotional engagement, lights up the entire posterior region, the occipital, temporal, and parietal lobes. Stage 2 is reflective observation. The raw sensory data moves to the temporoparietal junction, the brain's association zone, searching for connections to existing long-term memories. If an instructor doesn't provide a deliberate pause for reflection, the signal dies out before it can integrate. Stage 3 is abstract conceptualization. The signal pushes into the prefrontal cortex, the brain's executive center. This is where working memory assembles the raw data into geometric logic, rules, and testable hypotheses. Finally, stage 4 is active experimentation. The signal routes to the motor cortex, sending commands down the spinal pathway to speak, write, or build. Without physical or verbal output, the circuitry loop remains unclosed. Wrapped around this cortical cycle is the limbic system. The amygdala acts as the chemical gatekeeper for the entire process. If the academic environment triggers fear, extreme stress, or humiliation, the amygdala blocks the neural signals from reaching the prefrontal cortex. The student is forced into a fight or flight state of mechanical memorization. Conversely, the joy of discovery or a manageable challenge triggers the release of dopamine. Beyond improving mood, dopamine actively drives the neuroplasticity and memory consolidation required for learning. Bypassing any single stage of Kolb's cycle, or ignoring the emotional state of the room, leaves the student's neural circuitry physically disconnected and incomplete. This biological framework led to the most famous and most misunderstood byproduct of Kolb's work, the 4 learning styles: divergence, assimilators, convergers, and accommodators. For decades, educators have subscribed to the matching hypothesis. This is the belief that instructors must diagnose a student's dominant style and tailor their teaching to fit that specific profile. Modern meta-analyses have dismantled this. The matching hypothesis is a neuromyth. Evidence shows that catering to a student's preferred learning style fails to improve academic outcomes. The core flaw is treating cognitive preference as a fixed trait. In reality, a student's approach fluctuates dynamically depending on the exact task, the context, and the environment. The true objective of higher education is learning flexibility. We should move away from diagnosing fixed styles and toward actively stretching a student's capabilities. Think of it as cognitive cross-training. We force the pragmatic, action-oriented engineer to practice deep, divergent reflection. We require the imaginative humanities student to construct rigid, logical models. A professor's job is not to coddle a biological preference. It is to deliberately force students into their cognitive deficits, building resilient, generalized competencies that hold up under pressure. The logistical challenge is obvious. Running 200 students through an individualized cycle of physical experimentation and deep reflection seems impossible in a massive, tiered auditorium. To bridge this gap, instructors use problem-based exposition. This is distinct from traditional group-based problem-based learning. In problem-based exposition, the lecturer acts as a live cognitive model. Instead of just delivering the final theorem, they work through a paradox in real time. They outline the dead ends, discard false hypotheses, and deduce the theory live on stage. Students empathetically map the lecturer's cognitive cycle within their own brains. They experience the reflection and conceptualization vicariously, tracking the logic step by step. An even more aggressive, scientifically validated approach is Manu Kapoor's methodology of productive failure. This chart compares traditional direct instruction with productive failure. In Kapoor's model, the sequence is intentionally reversed. Students are forced to attempt a complex, novel task completely unsupervised before they are given any theoretical framework. They inevitably fail or invent suboptimal solutions. This suboptimal attempt reveals a severe knowledge gap, causing the amygdala to flag the missing information as a high-priority need for survival. When the instructor finally delivers the theoretical lecture, it falls onto neurologically plowed ground. Students compare their failed attempts to the canonical solution as the instructor speaks. These methodologies don't rely on being entertaining. They work because they artificially engineer the exact chemical and cognitive friction required to force neuroplasticity. If we update the pedagogy, we have to update the metrics. Standard exams are highly limited. They measure only one isolated quadrant of the cortex, abstract conceptualization, the raw recall of facts and theories. To measure true competency, institutions evaluate the invisible processes. Using analytical rubrics, they grade the depth of reflection, the quality of their prototypes, the rigor of their search during a productive failure. There are strict guardrails to this approach. Cognitive load theory dictates that too much unstructured discovery will immediately overwhelm a novice's working memory, shutting down the learning cycle entirely. Instructors must also navigate cultural constraints. Demanding active experimentation and open debate with an authority figure can cause severe cognitive friction for international students originating from high power distance cultures. Implementation must be specific to the discipline. While engineering relies on crash test simulations to initiate the cycle, the humanities require a completely different entry point. Instead of a passive lecture on the Yalta Conference, history students are assigned national profiles and forced to simulate the negotiations. This creates a high-stakes concrete experience, generating the raw emotional material for later document analysis. This aligns directly with universal design for learning. We deliberately push students out of their comfort zones while providing multiple, accessible entry points into the cognitive cycle. The directives for modern educators are clear. Design full cyclical experiences. Engineer situations where mistakes serve as valuable raw data. Manage the limbic biochemistry of the room, and demand cognitive flexibility over stylistic comfort. This shift transforms the university from a credentialing center into an environment that physically re-engineers the human mind for a lifetime of learning.